All right. This problem looks like something different. Because rather than being a roller coaster problem, we're talking about a hill problem, but it turns out there are some rules that I gave you in the study guide that still apply. So one thing I want to say is, at the top, down is still positive. Okay? The other thing is we're talking about a minimum height of the hill, which is a disguised way of saying there's going to be some speed. And if we go below that speed, we're actually going to have a normal force on the car. So we're still doing a minimum speed problem. And that implies that the only force acting is mg, or gravity. So what does this mean? Let's draw the free body diagram. We have the normal force pointing up. We have the weight pointing down. Now let's be really clear. We said that at the top of a loop, down is positive. That rule still applies. So we're going to take weight going down minus the normal. Ask yourself, why am I subtracting the normal force? And the answer lies in this idea that at the top of a loop, downwards is the positive direction. So ask yourself, what direction is the normal force pointing? And if you arrive at that answer that it's pointing up, that's why you actually have to subtract it. And so we have mg minus the normal force is mv squared divided by r. Now here's what we're saying. The normal force when we're at our minimum speed is 0, just like the rules that we used on the roller coaster problem before. So now let's plug in our numbers. We have 1,250 times 10 equals 1,250 times 20 squared divided by our unknown radius that we want to solve for. We're going to use that radius to get height. I'll show you how in a second. So when we isolate r, we end up getting 40 meters per r, but that's not our answer. So we have a radius of 40. That's this whole length here as 40, but let's be clear. We're told that we have the center of our circle buried deep in the ground. This is 15 meters. So what this implies is that 15 plus the height that we want to solve for gives us 40. So our hill is actually only 25 meters high. Now for part B, they ask us the car rolls down the hill in neutral with no engine to power it. We'll use conservation of energy to find the speed at the bottom of the hill. Now what we're saying is this. At the top of the hill, and I'll redraw this again, here's the car, we have speed greater than 0. We have v greater than 0. And sorry, I just chucked a box of tissues at poor Devin because I was recording, but now my cover's blown. And he scowled at me, or he looked surprised. He thought I was being mean to him. And I'm sharing that with all of you listening to this video because I felt really rude because I was actually trying to be nice. So sorry, Devin. All right, cool. All right, back to physics. So v is greater than 0. And at the top, h is greater than 0. Now, at the bottom of the hill, we only have v greater than 0 and h equals 0. So at the top of the hill, we actually have kinetic and gravity. At the bottom, we only have kinetic energy. So we're going to use E initial equals E final. That's our conservation of energy formula. So we have E kinetic at the top plus EG. And that ends up being converted into all E kinetic at the bottom. So this formula I give you, this one you'd actually need to be able to come up with, and you'd be able to need to draw this picture and figure that out. So we have 1/2 m v at the top squared plus m times g times h equals 1/2 m v at the bottom squared. One thing I want to point out, the m's actually cancel. So I'm going to go ahead and do that. So I have v at the top squared, which is 400 over 2, plus 10. Now the height we got is 25. and that's going to equal 1/2 v at the bottom squared. So kind of continuing on here, I'll just kind of finish it here. We'll have 200 plus 250 equals v bottom over 2 squared. So we end up getting 900 equals v bottom squared. So we get 30 meters per second for v at the bottom. That was actually totally coincidence. That's kind of cool that it worked out that way. Nice whole number. Now, if the car is only going 5 meters per second at the top of the hill, we want to know what the normal force is in the car from the ground, so let's set this up. We've got normal going up, weight going down, and we go back to the solution that we used in the first part. So we have weight minus normal equals MAC. So we have mg minus n equals mv squared over r. Let's keep going here. Remember, the radius is 40, which we got from before. So we have 1,250 times 10 minus the normal force equals 1,250 times 5 squared divided by 40. So I can actually subtract off. Normal is 12,500 minus, and let me just calculate what this thing here will be. So 1,250 times 25 divided by 40. That's going to be 781.25. And so when we actually get our normal force, we're going to actually end up getting 11,719 newtons of force. All right, so that's question C.